So I present
Perfect.
to you Enzo Bonacci, mixing optimization in the batch crystallization of CAM. Thank you very much.
Exactly. Thank you. It's always a pleasure to be here for this, the Pearl of the Black Sea. Each year it is a real pleasure. So thank you to the organizers. Last year we explored the first part of old experimental study, and now we complete such survey. So in 1997, there was a gap in the knowledge of the production of the citric acid monohydrate. Why? Because there were a lot of studies about the kinetics of nucleation and crystal growth, but very few about the industrial aspects of the CAM production, where in stirred tank reactors, we will call them STRs, stirred tank reactors. So La Sapienza is the largest university in Europe, and in the 90s there was the Department of Chemical Engineering which decided to focus, to study, to test the industrial production of the CAM. Among the people who participated in that cutting-edge experience, there was also the author, under the supervision of Professor Barbara Mazzarotta. So, we had 3 STRs with different shapes, and last year we discovered how the best shape was the hemispherical, was the rounded shape. We studied with experimental tests and with computational fluid dynamics, and with a QBasic program we coded ad hoc. The resulting thesis and research papers were acknowledged as pioneering more than a decade later. You can see a general reactor here, but this is the real reactor we used, and it was the optimal shape, so the round shape, and such conclusion, I remember the talk of last year, was probably beyond the substance we chose. So it is always true that in a batch crystallization of a substance, the round shape gives the best performance. We proved it last year. This year, this talk is focused about agitation, the mixing, which is the best mixing in order to obtain a good and optimal crystal size distribution, CSD. What does it mean? It means a homogeneous distribution of large crystals. So what did we find in 1997, 1998? We found that a 3-blade marine propeller is the best one, and a low speed in a buffered tank can ensure the best product. Such conclusions were experimental, but confirmed by computer simulations. Now, we must just recall a particular formula that is called Zwitterin correlation. The Zwitterin correlation is a very complicated formula which gives the just suspension speed. We will treat it in the next slides. So, the first thing was to choose the best impeller. We had two very similar impellers, the Rushton turbine and the three-bladed marine screw. One gave radial flux, the Rushton turbine, whereas the three-bladed marine screw gave the axial flux. Well, using the switching correlation, we found that only the three-blade marine impeller provided a sustainable steering rate, allowing energy saving and system stability. How did we find it? In this way. So we simulated the fluxes. You can see the three-blade marine impeller on the left with the axial flow, and you can see the Rushton turbine on the right with the radial flow. Here there are some datas. Those are the tank-independent datas. And here the tank-dependent datas. All of them were put inside the formula, the switching correlation. And the output was the NJS for the Rushton turbine was very high, around per minute. Whereas the NJS, the jet suspension speed, given by the switching correlation for the marine impeller was the half, exactly the half. The high jet suspension speed of the Rushton turbine implied a great energy consumption and an instability of the rotating system, and a very annoying noises, very strong noises. We were in the laboratory and other people said, so what's going on there? What's happening? Is there something broken? It was a very high noise. So we chose the marine impeller and we assumed 740 round per minute as minimum agitation speed, ensuring the suspension of the precipitate particles. It was confirmed by the computer fluid dynamics. In 1995 was released the Visimix software, and we were very quick to learn how to use it, and it confirmed that the best simulated flux lines were given by the three-bladed marine impeller. Once chosen which kind of impeller, we had two alternatives: a high speed or a low speed, and we could choose just testing them. So we found that the three-blade marine propeller is the best agitator. We found that the agitation speed optimal is around 2% above the minimum value for the solid suspension. And the other conclusions that we already treated last year about seed crystals, about seeding temperature, and about the geometry of the tanks. We did not insist about them. Just focus about the agitation. Following the strict protocol, a strict test protocol, we carried out 20 tests. And you can see the orange column when you have low steering rate, and you can see the green column where you have the high steering rate. Oh, it is a very marked difference. You can see all the data you need when you treat fluid dynamics, so Reynolds number, power, etc. And the most important thing, which was the best crystal side distribution? It is the curve in red. It is the curve on the right. and it was given by a low stirring rate, always, in any conditions. So we interpreted our tests. The low agitation was the best. Why? Because the attrition slowed down the crystal growth by splitting agglomerations, and there was another nasty phenomenon, the secondary nucleation by collision, recognized for its quadratic growth with respect to the impeller speed. So it was necessary to keep low the impeller speed in order to have a crystal side distribution we wanted, so large crystal and homogeneous. But we also wanted to simulate with a program written by our own hands, and we started from an already existing program which was focused on potassium sulfate. Well, the program in QBasic written for the citric acid monohydrate took months to be completed because there were two subroutines, very difficult, to be implemented for the agglomeration and the secondary nucleation by collision. But the result was quite accurate. It didn't work only when the seed is heavy, but it is not an industrial practice. So we can see that the program is optimal when you treat the industrial practices. You can see the difference between the data and the simulated curves, very similar, and it is confirmed that you must keep a low steering rate in order to get the best crystal side distribution. And we can reach the conclusions. In the year 1997-1998, at AGMA laboratories of La Sapienza University, we analyzed the batch cooling crystallization of the citric acid monohydrate from aqueous solutions. The choice of a 3-blade marine impeller optimized the process, allowing energy savings, stability of the rotating system, and low background noises. Looking for a homogeneous distribution of large crystals, we found that an agitation slightly above the just suspension speed established by the deuterium correlation was the most effective to reduce the negative incidences of attrition and secondary nucleation. The experimental work was supplemented by a QBasic program to predict the CSD and the Visimix software to simulate the fluid dynamics inside each buffered crystallizer. Years after such work, there was some recognition, like from the Italian Physical Society, the International Year of Chemistry, the Magna Grecia Prize, and other conferences. And least but not least, the AGMA conference, which is giving the opportunity to valorize an old work carried out in laboratories in Italy, in Rome. Sometimes the researchers are all day closed in laboratories from dawn to sunset, and they ask themselves, are we doing something interesting? Well, in this case, we can say yes, it was a pioneering work about this particular substance, the citric acid monohydrate. Here you have the references and the image credits. And that's all. Thank you for your kind attention.
Thank you very much, Enzo.